Spherical mirrors. Look at yourself in a spoon. The image changes as you switch from the side that curves outwards to the side that curves away from you. What you just observed were the laws of reflection in action, and they get a lot more interesting when we deal with curves rather than straight surfaces. To keep things simple and fun, we will focus on a specific type of curved mirror, the spherical mirror. Spherical mirrors look like they were sliced out of a hollow sphere. We chose them because the geometric principles behind their working are already known to us. Combine that with the basic laws of reflection that you have already learned, makes understanding image formation in these mirrors a lot simpler. Before we proceed, let's familiarize ourselves with some standard definitions when we talk about spherical mirrors. The convex mirror. A mirror whose reflecting side bulges outwards is called a convex mirror. The concave mirror. A mirror whose reflecting side curves inwards like a cave is a concave mirror. Let's understand the rest of the terms in reference to a concave mirror. Here is a concave mirror. It is the part of a hollow sphere. When we look at it from the side, what we see is the arc of a circle. That circle has a center, which is the same as the sphere of which it is a part. And this center is better known as the center of curvature. If we were to draw a line from the center to the surface of the mirror, we see it as the radius, and we call this the radius of curvature for this mirror. Looking at the definition of normals, we realize that the radii of this sphere each represent a normal for the point where they meet the surface of the spherical concave mirror. The geometric center of the mirror surface is known as the pole. An imaginary line passing through the pole and the center of curvature is called the principal axis. All the measurements are made on the principal axis with respect to the pole. In convex mirrors, the same arguments apply, only the center of curvature and the radius of curvature now originate behind the mirror. Having defined all these terms, if we now draw a tangent at the point where the radius of curvature meets the surface of the mirror, we notice that as expected, they are perpendicular to each other. This is a fundamental property of circles and spheres. Now, if we were to take rays coming from an infinite distance away, meaning that these rays would all be parallel to each other, the incident rays on the concave mirror would be reflected in such a way that they converge or come together at the focus. For this reason, concave mirrors are also called convergent mirrors. To converge means to come together. The focal point of this mirror is thus where the parallel rays from infinity meet each other after reflection from the surface of the mirror. Since these rays are meeting at an actual physical point in front of the mirror, the image is said to be real. Conversely, rays hitting a convex mirror will diverge away from each other, which is why we call them divergent mirrors. The rays move away from each other, they diverge. In this case, the reflected rays appear to originate from a virtual point behind the mirror. Thus, they form a virtual image. Please note, the human eye is completely unconcerned with the actual location of the object. It is only concerned with where the rays of light seem to come from. In the case of the convex mirror, we see that the rays seem to be originating from some imaginary location behind the mirror, even though no light is actually coming from this point. But to our brain, it makes no difference. It interprets the image to be originating from behind the mirror.